Hello everybody, welcome to this video on Boolean functions represented in the form of logical diagrams. So as explained earlier, the various circuits, digital circuits in the computer can be easily represented in the form of Boolean functions. So there will be some input, and then based on what that logic circuit is supposed to do, we get certain output. So we need to represent these Boolean functions in the form of logical diagrams, in the form of gates and interconnection of gates. So let's see how we can do this representation. So in a logical diagram, so we have a function like this. F is, say, a simple one. Let's start fy x dash, xy z dash. Okay, so here each of this is a literal. Each of this is called a literal. So each of these literals will be an input to some gate. Okay, and when we had discussed about logic gates, we saw only 2 input logic gates. Now a logic gate can take more than 2 inputs also. So one way of representing this would be, as I said, each of these 3 literals will be input to the gate. So I have x, y and z. Okay, now z has to be complemented, so for that we pass it through the NOT gate, which is the inverter. So z goes as input, and what comes out here is z dash. Okay, and then x, y and z dash are the operator among them is the AND operator. So I can write it like this together and then put a AND gate out here. So the output of this would be x, y, z dash AND. So x, y, z dash. And this is nothing but our f function. So in this way we can represent a Boolean function using logic gates. Now this example function that we saw was a simple single term function. We can have multiple term functions also. Let us take another function, x plus y dash z. So here I have 2 terms. So x is a literal. So let me just put down the literals. X, y dash and z. So these are our literals. And each of this is called a term. Okay, so each of this is a term. Now in our first term here x, it consists of a single literal. There is no other operator with it. There is no AND or. So it is a single literal term. Whereas the second term, as you can see, y dash z, so we have 2 literals here, and in this term there is an AND operator and also there is a NOT operator. So each term will be can be implemented with the help of a gate. So for each term we have a gate. Each literal will be input to some gates. So let us see how this can be implemented. So I have first, let me have, so this is x, this is y and this is z. Now y has to pass through an inverter to get y dash. Okay, so y dash and z are combined by a AND operator. So I get y dash z here. Okay, and the first term, that is this and this, so x is here, this is my first term and this is my second term. These two are connected by the OR operator, OR gate, OR operator. So I am going to use a OR gate with this. So okay, so this is the OR gate. So what I get here is x OR This is x, that is the input which is coming to this gate, x, or what else is coming? Y dash z. So this is our function f. Let me take a slightly more complex, with more function with more terms. So let me take this function. F is x dash y dash z plus x dash yz plus xy dash. So here we have lots of literals and 3 terms. So let us implement this. So first I have, for each term I'm going to use a gate. Okay, each term I'm going to use a gate, and these each literal would be inputs to the gate. And if x is the input, I'm going to pass it through a inverter. Okay, so x, so what I get here is x dash. All right, now y, also I need y dash, so y also I'm passing it through an inverter. Z, okay, I don't need the term z dash, so I'm not using an inverter. Now let's see how we can combine. So let's take the first term, that is x dash y dash z. So x dash is this part, y dash is this part, and z is this. So how are they combined? They are combined using a AND operator, so an AND gate. So what I get here is x dash y dash z. Now the second term is x dash y z dash, z. So x dash is coming from here. I don't need to write x dash again, so I can just, whatever this portion, that is whichever is here, this is x dash, and what is this side is your x. So I need x dash. Okay, I get x dash. I need what? Y. Now y, which is y? This part is y dash, so this part is y. So I will bring y here, y. And what else do I need? I need z. Okay, so I can just bring it from here, because this part, this whole thing is z. This is z, so I can just bring it here, and of all this. So what I get, what is, you can see, this is coming from x dash, this part is coming from y, and this part is coming from z. So what I get is x dash y z. And finally I have third term, that is x y dash. So x is here, x, and y dash. Y dash is I can bring it from here, y dash. So x y dash. So I have the 3 terms coming out from these 3 gates. Now I have to combine all 3 of this, and the operator is plus, which is OR. So I can have one OR gate which will combine all 3 of this. So I get x dash y dash z, or x dash y z, or x y dash, which is our function f. So this is the logical circuit for the function f. So in this manner you can draw different types of diagrams, for logical diagrams, to implement our Boolean function. One thing to be noted out here is that, as you can see, the more the number of literals, the more complex the gates become. More literals and more terms, more literals and more terms in the Boolean function, they give rise to more complex logical circuits. Okay, and we have already seen that you can have, to represent the same logic, you can have multiple functions. The same function, this function can be written with smaller number of terms or and lesser number of literals. So if the work remains the same, the function remains the same, but what we are doing is we can reduce the number of literals. We are reducing the number of literals, or we are reducing the number of terms. Okay, then what happens? The gates or the logical circuits that we can draw now would be less complex. And it is not just about complexity, it is also more gates means more space will be taken inside the circuits. More heat will be generated inside the circuits. More power will be consumed inside the circuits. So to avoid that, we would like to have simpler logical circuits with lesser gates, and each gate taking lesser number of inputs. So what we can do is we can try to minimize the Boolean functions, minimize our Boolean functions such that the number of literals is reduced and the number of terms is reduced. So in the coming few videos, we will see how we can go about this minimization of Boolean functions.